Hello and welcome to this tutorial. Today I would like to discuss the notion of a probability measure. This notion of probability measure is going to give some mathematical definition to the notion of probability, and also this probability measure will be useful later on when we define the probability mass function as well as the probability density function. So let's start off with just a simple example. So suppose we have a random experiment of a coin toss. Suppose you just toss a normal coin, unbiased coin. So we have two possible outcomes of that experiment. These outcomes are heads or tails. And the probability of heads, which we can write as probability of heads, is equal to zero point 0.5. And similarly, the probability of tails is also zero point 0.5. Probability of tails is zero point 0.5. Also, the sum of these two probabilities is equal to 1. The probability that we get either heads or tails is equal to the probability that we get heads plus the probability that we get tails, since we either get heads or tails, which is equal to 1. So before we can define a probability measure, we need to first define two important notions in probability. The first one is omega, the sample space. So omega is the set of possible outcomes of the experiment. The set of possible outcomes of the experiment. So in the case of a coin toss, omega is what? So in the coin toss, we have two possible outcomes, either heads or tails. So omega is a set consisting of two elements, heads and tails. So the element heads and the element tails. Another notion that we need to define is the Borel field, F, Borel field. The Borel field will allow us to take probabilities of events. So suppose you want to take the probability of heads, the probability of heads and tails, or the probability of neither heads nor tails, which is an event with probability 0. So to do that, we define the Borel field, which is a collection of subsets of omega, and as we will discuss in a minute, we will take the probability of these subsets. So Borel field is a subset, sorry, it's a collection of subsets of omega. It's a collection of subsets of omega that are closed under union and complement. So you could look that up later, but the simple idea is that we want the collection F to contain the possible events that we would like to take the probabilities of. So, for example, in the case of a coin toss, we would like to know the probability of heads, we would like to know the probability of tails, we would like to know the probability of heads and tails, that event has heads and tails, and also the probability of neither, which is the empty set, which has the probability of 0. So technically, a Borel field has to satisfy a more stringent condition, which is that if A1 up to AN are in the field, then the union of these A's, if A1 to AN, so the union from N equal to 1 to capital N, has to also be in the field. Also, the intersection of events A1 to capital N has to be in the field, and N can be countably finite, can be countably infinite, sorry. We could map them to the natural numbers, and they are all in the field, then their union and intersection must also be in the field. So back to the probability measure. So the probability measure P, sometimes we can write P or just PR. Here I used PR, so I'm just going to stick to that. So the probability measure is a function from the Borel field F to the interval 0, 0, 1. So we are assigning real valued numbers between 0 and 1 to events in F, or members of F, which are also known as events. And this assignment has to satisfy the probability axioms. So it has to satisfy the probability axioms. Axioms, which are 1. The probability of an event is non-negative, which means it's greater than or equal to 0. 2. The probability of omega is equal to 1. Why? Omega is the set of all possible outcomes, so the probability of omega has to be 1. And 3, if A and B are disjoint events, this, let me correct this, disjoint events, which means A intersection B is the empty set, then the probability of A union B, or the probability of A happening or B happening, is equal to the sum of the probability of A plus the probability of B. So for the case of the coin toss, you can see that these axioms are satisfied. So to summarize, we want to define a notion of probability. To do that, we had to define a sample space, which is the set of all possible outcomes of the experiment. Then we had to define the Borel field, which is a collection of subsets of omega. This allows us to then assign probabilities to those subsets. And for those probabilities to satisfy an intuitive understanding that we have about things that can happen, they have to satisfy these three axioms. That is, the probability is non-negative, the probability of omega is 1, and the probability of disjoint events is equal to the sum of those events individually. The probability of the sum of those events individually. I hope you found this video useful.